Hello, today I'm going to be talking about one of the most foundational machine learning algorithms for modeling linear datasets, and that's called linear regression. Let's start with a classic example of a task that we want to do for supervised learning. That's house prices. Imagine we want to predict a label, the house price. Again, this is a supervised learning problem because we have the answer right here, the label. Um, And imagine what we have is the features. So we know what the number of bedrooms are, the location, the size, if whether there's a pool or not. There's a bunch of information or features that we have, in which our objective is to use these features and find a relationship between these features, a relationship between the number of bedrooms, the location, and the size, and the house price to finally predict the house price, because that's our end goal. We can see this as a mapping. We want to map our input, which is the number of bedrooms, the location, and everything, and to our output, which is the house price. So we want to find some kind of pattern or relationship or rule that connects the two. And in this case, let's just assume that this relationship is linear because, generally speaking, more bedrooms or a larger house size would give a larger house price, so more pricier house in general. So how do we model this then? Well, we can use the basic simple linear model. In this case, if you see the linear equation here, we have y equals mx plus b, where y is what we want to predict, uh, the house price or the label, x is the input or feature, and m and b are parameters or the slope and the intercept that we want to sort of modify and adjust such that this equation can be true. So if we model this as a graphical problem, then we can see that it's sort of like finding a relationship between the x and y. In other words, y is a function of x, a linear function to be exact. Our objective is to choose good m and b parameters. So what we know, what is static or what is fixed is x and y, because obviously there's already a set house price, already set number of bedrooms and all that. Our goal is to find a relationship between them such that for new ones, we can predict the house price again. So we want to find a pattern that applies for all house price pairs. In this case, in our linear relationship here, our linear relationship is defined by the parameters m and b, which we learned during training. Um, Imagine that y is 5. The real answer of y is 5. And our input is 1. If we choose the m or the slope to be 2, then the predicted y would be 2 times 1 is 2. So again, it's not that accurate. But if m is 4, the predicted y is 4. So as you can see, this is fundamentally an optimization problem. We want to find the optimal m and b such that we make the parameters such that we can make the y as accurate as possible. If we graph this, we can see an interesting pattern emerging. This is in the 1D case, of course, where the x-axis represents the features, where in our house price example, we can see it's probably like the number of bedrooms or whether there's a pool or not. That could all be x. And the y-axis over there, that's our label, the house price. What I've done is I've plotted several points or pairs onto the graph, and they represent our data points. For instance, the first one looks like it's around a 1 for the input, and then it's 4 for the output. Given that, we want to find a relationship between each x and y pair. And we do that by fitting a line of best fit. As you can see, the first graph, we chose a really bad m, a really bad b too. It's completely opposite to what our actual pattern is. So we It's a poor fit. An okay fit is in the middle. In this case, we've chosen a solid but not perfect uh, choice of m. So the slope is, generally speaking, it's generally aligned with the thing, but it's just slightly off. And a good fit would be the one on the right, where the slope is almost is accurately modeling the one of the actual data set. Let's move on to multiple linear regression. Imagine each feature is graphically like a dimension, where 5 features, for instance, would be 5 dimensions, a 5D uh, problem. This works because, as you can see back here, this is the 2D plane, right? There's an x and a y. In this case, it's simple linear regression in the sense that there's only one feature, the x-axis. If we add more and more axes or features, then it naturally becomes a multi-dimensional problem, in which the linear model is thus a hyperplane that we want to fit inside that. The x-axis is the features and the input, and the y-axis is the label or the output. Because we want to find a rule and make a prediction, we can sort of generalize this rule, not just to one feature, but to multiple. This is much more informative because instead of just predicting, say, the house price using just the number of bedrooms, for instance, we can account for the number of bedrooms, whether there's a pool or not, the location, the roof size, many other factors that might actually go into the price, not just one. Because in the real world, uh, the label often depends on multiple stuff, not just one simple direct relationship. So multiple linear regression, which it is called, is about generalizing this to n dimensions or n features. And what we do is if we have features x1, x2, all the way to n features, xn, and a corresponding m for that, corresponding weights for that, then we can see this as a sum, a weighted sum, or a linear combination of the features. So what really is m and b in machine learning terms? In algebra, we learn that m is like the slope, and it controls the steepness of the line. But and in multi-dimension case, it can be seen as a partial derivative. But in machine learning, we can also see it as a control, as it controls the importancy or the importance of the sensitivity of the feature. In which case, the more steep slope would represent it has more influence on y, because a smaller change in x would induce a large change in y. So the feature, imagine a feature x1 with weight m1, imagine that had a weight of 5. That would be much more important than a feature with, for instance, a weight of 0.6, because the weight is naturally larger. And because the partial derivative or the slope at that for that specific feature is much more steep, much higher, it has it's more sensitive in terms of y, so it has more influence on it. The bias or b is basically the y-intercept. It's the baseline value if everything else was kept 0. So how do you make a linear prediction out of this? If you have adjusted these m and b parameters to be good, then for a new data point, you can use these parameters to generate a prediction. For instance, if you found m was 5, so that is, the price is 5 times that of the size, then if the size was 10,000, then the price would be 50,000. So how do we know if our predictions are good or bad? As discussed before, we need a loss function for this, or a way of measuring how off or how wrong our prediction is. The residual is basically the difference or the deviation of the prediction to the true answer. So it's true y minus predicted y. But there's obviously a problem, because if the predicted y is larger than the true y, that's negative loss. So turns out that negative loss is because it's very low, it ends up looking very, very good. So the model will be encouraged to make large predictions. To make this absolutely fair, we want to square it or make an absolute value to cancel negatives, because we don't care whether the prediction is larger than or smaller than the actual answer. We just care how close it is to it. Once we take the mean of that across all data points, we can account for the error or the loss for the entire data set, not just one. The common loss functions include mean squared error, or MSE, which we just talked about, which is basically, as you can see, it's summing it all up, the squared differences, and then dividing it by the number of data points. That's just the mean. So it's just the difference between the answer, f of xi, and the prediction, and then squaring that, and then taking the mean of that across all data points. The other method is to use mean absolute error, which is just the same thing, except we take the absolute value instead of the square. Root mean squared error, or RMSE, just takes the square root of MSE. Why we do this is because when mean squared error squares the things, it becomes the units are not on the same scale, because now suddenly we're operating in squared units rather than the original units. To normalize this back to our original units, we have to square root it. Linear regression has many applications involving supervised regression tasks that are inherently linear by nature. These could include house prices, sales and revenue projection, and salary prediction. But the key assumption that underlies all of this is that the data must be linear,